let's talk about the end behavior of rational functions. Now, before we begin, I want to remind you that rational function, a rational function is just a polynomial divided by a polynomial. Okay? So if you look at example 3, we've got like a linear polynomial divided by a linear polynomial. In part B, we've got a quadratic polynomial divided by a cubic polynomial. These are both examples of rational functions. And the key idea when dealing with rational functions is that look at the leading terms of the numerator and the denominator. Okay, those dominate. All right, so for example, if I were to look at the leading term of my function f of x, the biggest power is 2x. Well, the biggest power is x, so the leading term is 2x. Similarly, the leading term of the denominator is going to be 3x. So this function, for very large values of x, basically those leading terms dominate. So our function basically looks like this. So we can basically guess that our function, when we go off to infinity, is going to approach 2/3. Now, this is just how I think about the problem. When I actually go to solve the problem, I need to calculate a limit. So I'm going to take the limit as x goes to infinity of 2x minus 1 over 3x plus 4, and I'm going to multiply by 1 over the highest power in the denominator. So in this case, it's going to be 1 over x and 1 over x. So multiplying top and bottom by the same thing effectively multiplies my rational function by the number 1. So I'm not changing anything. So I take great care to distribute properly, and then I get the limit as x goes to infinity. I'm going to get 2 minus 1 over x divided by 3 plus 4 over x. And now we have that situation again when the numerator is constant here and the denominator is getting bigger and bigger and bigger. Same thing on the bottom. The numerator is a fixed constant of 4. The denominator for this particular fraction is x, and that's exploding off to infinity. So in both of those cases, each of those guys is going to go to 0. So the end result I get is we get an answer of 2/3. Okay. So I have a couple of comments to make. My first comment is that, y equal to 2/3 is a horizontal asymptote. The second thing I wanted to mention is that we get the same result if x goes to negative infinity. So we have both of those things happening. All right, I'm going to highlight this answer of 2/3, and really this y equal to 2/3 is a horizontal asymptote is the ultimate result. Let's take a look at example B, example 3b here. Let's think about it first before we formally calculate any limits. So when I think about this guy, the leading term for this guy is basically 2 times x squared. And the leading term for the denominator is basically x cubed. So when I simplify this down, this guy basically behaves like 2 over x. Okay. And we can tell that as x goes off to infinity, this whole fraction here is going to go to 0. So I'm anticipating that this function g of x will have a horizontal asymptote at 0. However, let's calculate it for real by using limits. So we're going to calculate the limit as x goes to infinity of 2x squared plus 3x, all divided by x cubed minus 4. Just as before, I'm going to multiply by 1 over the highest power in the denominator. That's 1 over x cubed and 1 over x cubed. After distributing, I get the limit as x goes to infinity of 2 over x plus 3 over x squared. That's the numerator. The denominator is going to be 1 minus 4 over x cubed. And now you see I have 3 separate situations where the numerator is a constant, but the bottom is exploding off to positive infinity. All right. So in each of these cases, this goes to 0, this goes to 0, and that guy goes to 0. So when I simplify, I get 0 plus 0 over 1 minus 0. That just gives me 0. And that's going to be my answer. Okay. So we have a horizontal asymptote at y equal to 0. All right, great. Let's take a look at one more example over here. Before I move on, I should probably point out that this whole argument works even if we go to negative infinity instead of positive infinity. So that doesn't change anything going to negative infinity. Let's take a look at this last one. When we take a look at this last one over here, what do I see? Well, the leading term of the numerator is basically 3x to the 12th power. And the leading term of the denominator is basically 5x to the 4th power. So when I simplify those quotient of leading terms, I'm going to get 3 over 5 x to the 8th power. Okay? So let's do it for real. Let's calculate the limit as x goes to infinity of 3x to the 12th plus 4x divided by 5x to the 4th minus 7x squared. I'm going to multiply top and bottom by 1 over the highest power in the denominator. In this case, it's 1 over x to the 4th power. And after I distribute, I'm going to get the limit as x goes to infinity. We're going to get 3x to the 8th power plus 4 over x cubed in the numerator. In the denominator, I'm going to get 5 minus 7x squared. And when I take the limit as x goes to infinity, 2 of these terms, the 4 over x cubed is going to go to 0, and the 7 over x squared is going to go to 0. So I'm left with looking at the limit as x goes to infinity of 3 over 5 x to the 8th. And remember, we know what the graph of this guy looks like. If I were to draw a little picture over here, the graph of that is basically going to be a U-shaped function. So we can see that as x gets bigger and bigger, this guy is going to go to positive infinity. Similarly, if I took the limit as x goes to negative infinity of my function h of x, I hope we could see that this is going to give me positive infinity as well, because again, the leading term is this U-shaped object over here. All right, so let me highlight each of these answers. In this case, we have infinite limits for our end behavior. All right, everyone, take care.